Swayam Prabha. Digital India. Educated India.
Hello and welcome back. Today we are going to start with a new topic in our course or in our lecture series on solid mechanics or mechanics of materials, right? So in this particular lecture series, what we are going to learn are the different kinds of stresses and strains which can exist within structures subject to different kinds of loading. You will see in the later chapters or in the later topics that we will cover that when structures are induced to different kinds of loads, different structures have different kinds of loadings on them, you have all these different types of stresses which may arise as a consequence of these loadings, right? Now, depending on the load or depending on the particular structure, you may have these loadings occurring in different proportions. Analogically, it may be said it is very similar to maybe going to your kitchen and then learning the different ingredients which make up a particular recipe. For example, if you take a look into your kitchen, you'll probably have the very similar ingredients. Like, for example, you can have turmeric, you can have red chili powder, you'll probably have coriander, cumin powder, and so on and so forth. Now, suppose if you are making a recipe X, it requires a particular proportion of these different spices. If you're cooking a recipe Y, it requires different proportions of the same set of spices, right? Similarly, in structures, as I said, a particular set of loading on a particular structure will induce different kinds of stresses of the same building blocks. You may have tension, you may have compression, you may have shear, you may have bearing stresses, right, which we're going to learn about. Now, if you have another structure and another type of loading, or the same structure with a different type of loading, you will again have these kinds of stresses, but maybe just in different proportions, right? So let's go ahead and get started. For example, this is what you see on your screen is a person who is in the gym and doing exercise, right? Now here, if you take a look at this, you can understand that this is an entire system that you're looking at. Now, if you're taking a look at a particular system, and if you are breaking this particular system into the different components, so if this is the overall system which you're looking at, right, and if you take a different small portion of the system, and if you take a small element in this particular portion, you will see that that element has the different kinds of stresses which are going on over here, right? Now remember, in our last topic when we were talking about the introduction to the course Introduction to Solid Mechanics, what we had discussed that the overall deformation of any body essentially comprises of the deformation of these smaller tiny segments which are there. For example, if I have this particular sponge, again, the overall deformation of this entire sponge depends upon the individual deformations of the building blocks of this particular sponge, which in this particular example, you can probably guess as these boxes which are over here, right? So each of deformation of each of these boxes gives the final deformed shape of this particular sponge. Similarly, coming back to our example, the overall behavior and the overall deformation of this entire system, of how this entire system behaves, is going to be dictated by these smaller building blocks which are there, right? Now, if we take a look at this particular element over here, what are the different types of forces or the stresses which are acting on this particular element, right? So we can consider this also maybe quote unquote a system, and we can probably discretize it even further. For example, this particular building block is undergoing some kind of normal stresses over here, and from the action of the stresses you can tell that it is going to stretch over here. If these forces could be acting vertically down as well, in which case you will have a compression, right? And on these faces over here you have the shear forces which are also acting, and as a result of this you will have some change of angles in between the planes which are perpendicular. They are probably going into an oblique angle right now, right? So we have the normal stresses and the shear stresses, right? And also in addition to this, there is a particular type of stress which is known as the bearing stress. So if you take a look at the bearing stress, bearing stresses usually result from the contact. So for example, this particular place over here, so along this maybe entire bar, the place where you are touching, right? So what you're essentially doing, you're doing a contact stress. It's like a contact. So you're having, this is the bar, this is the palm of the hand. You're having some kind of contact stress. We'll learn more about the bearing stresses later. But most importantly, there are three kinds of stresses that we learned until now: normal, shear, and the bearing stresses which are there, right? Now, the rest of the topics in this particular or rather the rest of the subtopics in this particular under this particular topic, which will be divided into normal stresses, shear stresses, and bearing stresses, right? So first we are going to take a look at the normal stresses, which are essentially the tensile or the compressive stresses. So tensile and the compressive stresses together can be clubbed into the normal stresses, right? Now, can you, from your back in the day from engineering mechanics or structures which you normally see or normally heard of, or maybe solve some problems, can you give an example of a structure where the members of the structure are primarily subjected to only normal stresses, that is only tension and compression, nothing else, no bending, there is no bending in the structure, only tension and compression, right? Can you maybe take a few moments to think about it? Maybe some of you got it right. One classic example of this are trusses, right? So if you remember that when you had solved truss problems, in truss problems you take every individual member, you solve the equilibrium equations, and eventually what you get are the normal stresses, which are, or the normal forces, right? You haven't studied stresses yet, the normal forces which are acting in these individual members, right? What may be some of the other kinds of structures which are subjected to just normal or maybe primarily normal forces, right? For example, the building where you are in, where you're probably watching this video right now, the columns of the building are classic examples which are subjected to normal stresses, right? As you can see in the figure over here, this is a bridge column which is subject where on top of the bridge the vehicle goes, and this one takes the normal loads and transmits it to the foundation or the footing over here, right? These are the columns in the Mumbai Terminal 2 International Airport, these beautifully flared columns that you have, but it serves the same purpose of essentially transmitting a large amount of the normal stresses coming from the top all the way to the ground over here, right? Now, some more complicated examples which you probably have seen or maybe have overlooked. Next time you take a flight, you see that the whole aeroplane has, you know, different kinds of equipments, of which you have this landing gear over here, and you may also have a tow bar which essentially tows the your aeroplane back into the hangar, right? Now if you take a look at any of these elements as well, so the tow bar is essentially pulling, you will take a look at any of these elements as well, there is this normal stresses or the normal forces which are going on. So if we again remember that, as we had discussed, what we are very good doing as civil engineers are that taking a real life example and making an idealization of that one, trying to solve that, and then applying it back to the real system, right? So for any of these structures that you are looking at, and if you are studying about normal stresses, they can maybe simply be represented as something like this, right? You have a prismatic bar, prismatic meaning the cross section of the bar remains the same along the length of the bar, right? So for a prismatic bar subjected to two loads P and P at the either end, right? So this is a classic example of a bar under normal loads or axial tension or compression, right? So let's maybe, you know, dig a little bit more further into this. So what you essentially see is that you have a prismatic bar. So maybe here I will write prismatic, meaning that your cross section is same along the length, right? So that is the meaning of prismatic. So you have a prismatic bar of a particular length L, right? And to this, what I am doing is that I'm applying two loads P and P. It has to be in equilibrium, right? So if one end you're applying a force P, the other end automatically you have to apply the force P. Or if one end, remember our last example, if one end is clamped, if I pull it with a force P, I will feel a pull with a force P here as well, right? Now in this particular example, once you start, you know, pulling with a force P over here, your bar is going to expand, right? So you're going to see something like this over here. So what was originally L has now become L plus delta over here, right? Now if within this bar, if you take a particular cross section Mn, and if you draw the free body diagram of this particular part over here, right? If I chop off this particular bar about this particular cross section Mn, what you're going to see is something like this. Now remember, this is very important that previously when we had learned statics, you were drawing the free body diagram of the entire structure, because the entire structure was in equilibrium. You drew the free body diagram, solved for the forces. Now remember that within the body also it is in equilibrium, right? For instance, this bar over here which you're looking at, when you are applying this force P and force P, it is simply going an expansion, but the bar by itself is in equilibrium. So every segment of the bar is in equilibrium as well. So if I am chopping off a particular portion, and if I'm only considering this left end over here, this has a force P, right? So consequently, to balance that out, I must have a force P on the other side as well, right? Now, if you take a look at this particular cross section, this force P over here induces something which is known as stress, which is a normal stress, as you can see over here, right? So this normal stress, so in another way to explain that even if I'm pulling with the point forces over here, right, at every cross section it is undergoing the same amount of force, but that force is sort of smeared across the whole cross section. Although I'm applying maybe a point load here at a particular cross section, every material, every bit of the sponge is resisting that particular load P, right? So this particular load P essentially induces some amount of stresses across the entire cross section, and that stress is known as this normal stress over here, right, which is the axial load divided by the cross-sectional area. So in this particular case, if my cross-sectional area of this one is say A, let me call this as area, right? So this is going to be equal to P divided by the cross-sectional area A, right? But remember that it has little bit of assumptions. Now what are the assumptions? So what did we do when we wrote it as P divided by A? It is essentially, I'm just calculating the total load divided by the total area in an average sense, right? Now if you again take a look at this one, and I want you to observe very closely, if I'm taking this and I'm pulling it, look at these vertical lines at the ends and look at the vertical lines at the center. If you take a look at the vertical lines at the end, you will see they're having a kind of a curvature, whereas the lines at the center stays more or less the same, stays more or less straight, right? So what it essentially means is that when I'm applying these point loads at the end, I'm having some concentration of stresses over here, concentration of stresses over here, and as I am moving farther away from the point of application of the load that is near the center, the stresses more or less stabilize, and this formula of sigma equals to P divided by A can be easily applied. We will come back to this later. There is a particular concept or particular principle known as Saint-Venant's principle which deals with this, but for the time being, let's just be aware of this assumption that if you're taking a look at this particular bar, as you saw in this example as well, that towards the end where you have the points of application of the load, the stresses need not be average, need not be uniform. You cannot simply probably take the total P and divide it by the total A, but as you are moving away from this point of application of the load, this becomes more and more applicable over here, right? So in this particular example we studied, or in this particular slide, we studied this thing called the normal stress, right? Now what did we see when we apply the stress? What was originally L becomes L plus delta. So there is an elongation. Now in addition to stress comes its friend, which is the strain, right? So coming back to here, again going back to the same example, after pulling it with P, I have this L plus delta over here, right? So that leads to another quantity which is known as the normal strain. What we saw in the previous page was normal stress. This is normal strain, which is the change in length divided by original length. So this is simply going to be, my final length is L plus delta minus L, which is the original length, that is our change in length, the numerator, and the denominator is the original length L, so which is going to be equals to simply delta divided by L over here, right? So normal stress, the average normal stress, the quote-unquote average normal stress is P divided by A, and the normal strain is delta, that is the change in length divided by the original length L, right? Now you're probably thinking that whenever there is a stress, there must be a strain and they must all go hand in hand. But you will see that later. We'll talk about some examples where sometimes they can coexist without each other as well. Right? So let's move on to one particular axiom or one particular theory which is there, that if you have, let me just bring it up quickly. So what this theory says is that if you have a uniform stress distribution, remember that is P divided by A, then the line of action of the force, that is the line of action of this particular force P, must pass to the centroid of the cross section. So what it essentially means is that let's take a look at the figure and try to understand, is that you have a particular cross section over here, you have applied a particular load P, right? This you may imagine as the internal cross section Mn, right? So internal cross section after applying the load, every small bit of that cross section is undergoing that P divided by A stress, right? Which is this particular guy over here. Right? So what it says now, these arrows, don't be misled by them. These arrows are not acting only at the edges, it is acting throughout the entire cross section over here, right? So if I am looking, you know, from the front, and this is the 2D representation of the cross section. So essentially, let me maybe change the color of my pen. Yeah, so this cross section is essentially the same one over here. Right, and this P, the point where it acts over here, yeah, this point where it acts over here, this particular point is this particular point P1 over here. So let me maybe mark that one as well. So this particular point is P1, right? So what it says is that if the stress distribution has to be uniform, so for uniform stress distribution, this is the condition you have to satisfy. So for a uniform stress distribution, the line of action of this force must pass through the centroid of the cross section. Now there is a very easy proof to this one, right? So what I can do, so for example, if I am just focusing on this particular force P over here, so for P, what I can write maybe, so for P, right, if I am writing the expression for the moments about my x-axis, right, you have this force P which is acting out of this plane of the video you are looking at, right? If I'm taking the moment of the force of this particular force P about this particular axis x over here, it is simply going to be the force P times this particular distance y bar. And if you remember your right hand rule for the moment, it is going to curl, your thumb is going to curl towards a positive direction. So m of x is going to be this particular force P times, sorry, not y, it is going to be y bar, right? Similarly, m of y is going to be what? It is going to be, again, you are taking this particular force P over here, it is going to be times this x bar, but remember, this time your thumb curls vertically down. If you are going by the right hand rule of the moment, it is going to be minus of P times x bar, right? So this is for P, this is for, you know, this particular P which we looked at, right? Now if I try to write the same set of equations in terms of maybe the sigma over here, remember, which is the average stress throughout, right? And if I am focusing on a particular area, a small area, infinitesimally small area dA, so maybe we can write as for sigma, right? How do I write the expression for m of x? It is going to be the integral, remember, over this particular area dA. If my average stress is sigma, what is the force? Force is always stress times the area. So over this infinitesimally small area dA, the force which is coming is sigma times dA, right? And I am taking the moment about the x-axis, my distance is this y over here, so times y. Similarly, your m of y, the moment about the y-axis, must be minus of, the minus sign is for the same reason that your thumb for your right hand points vertically down when you're taking the moment about your y-axis, right? Is going to be minus of same sigma dA, which is the force, times x, times x over here. Right? Now technically this and this is the same because your section is in equilibrium, so this quantity it must be equal to this quantity over here. So if I have to kind of take both of these two together, P of my P of y bar must be equal to integral of sigma y dA, right? Similarly, my P of x bar, the negative sign goes for a toss, must be equal to integral of sigma x dA, right? Now remember that P is nothing but, if you take a look at this expression over here, this particular P is nothing but sigma times A. So if we replace, so this essentially means your sigma times A times y bar. Since sigma is a constant, that is a normal stress which is acting the same as throughout the cross section, I can make this come out of the integral, that is sigma integral of y dA, right? Similarly, this becomes sigma times A x bar is equal to sigma integral of x dA over here, right? So this thing and this thing cancels, this thing and this thing cancels over here. So what you essentially get is that your y bar is integral of y dA divided by A, right? And similarly, your x bar is integral of x dA divided by A, right? And these expressions, if you remember, right, both of these guys over here are simply nothing but the way that you compute the centroid. So these are the expressions for the centroids, right? So this proves this particular axiom which we are trying to prove, that for a uniform stress distribution, the line of action of the force must pass through the centroid of this particular cross section, right? Now that we have at least some concepts about the normal stresses, next we are going to look at a particular problem example. So the problem example that you see on your screen consists of two hollow cylindrical pipes which are connected by a cap plate. So this is a problem from one of your textbooks, the Gere and Goodnow textbooks, example 1.5. So you might as well, when you get time, just take a look there also if you want. So let me just maybe start marking or try to understand the problem first before or understand the system first before I pose the questions, and then let's see that how we go ahead and solve it, right? So what you have here are two hollow cylindrical pipes. This is the pipe 1, this is the lower pipe which is over here. So maybe just for starters I will go ahead and mark these guys. So this is my upper pipe and this is my lower pipe, right? So let's see what is given in terms of the dimensions and so on. So it says that the upper pipe has a length of 350 mm, it has an inner diameter of 51 and an outer diameter of 60 mm, right? And then the lower pipe, also a hollow pipe, it has a length of 400 mm, slightly longer than the upper pipe, and an inner diameter of 57 and an outer diameter of 63. Now just to demonstrate, this is probably a way to just imagine how it looks like. So maybe this is one pipe, this is one hollow pipe that you see, right, where you have, this is the outer diameter and this one is the inner diameter inside. So this is maybe the bottom pipe and you have a top pipe, right? So these are sort of connected together. Maybe if you put glue around the rims of that one, so it is sort of glued together over here. So you have a kind of a system, right? Now so you have two hollow pipes essentially. This is the upper one and this is the lower one as marked in this particular figure over here. Okay, now let's talk about the loads. It says, as you can tell, that the load PA, there is a load PA over here which is 7,800 newtons or 7.8 kilonewtons at the top, right? Now see how this load PA is being applied. So after you have sort of glued it, and remember the top is fixed over here, with some plate or something, right? So you are applying this load at this particular point in here at the juncture. You're applying this particular load, right? Now remember this load here is shown in terms of these smaller arrows, right? So these arrows do not represent the stresses, it is the total load. So maybe if I wrap my finger around it and try to apply the load, this is the total load which I'm applying is 7,800 Newton, and at the bottom you have another load PB which is acting over here. So maybe a way to imagine that, suppose if you connect a thread here and if you're pulling the thread, right? So that is the load PB over here. So I hope the system is clear to you. I will explain it once again. One hollow cylindrical pipe, another hollow cylindrical pipe, which is sort of welded together maybe, right? And the upper pipe is fixed somewhere, and the loads which are acting on the upper pipe is 7.8 kilonewtons, and on the lower pipe is a load, particular load P. Right. So now let's go ahead and let's see that what are some of the problems the question asks. Right. So the first problem, it says that find the load PB so that the tensile stress sigma in the upper pipe is 14.5 MPa. Right. So, and for this case, it asks, the part B of this question is what is the stress sigma in the lower pipe, right? So let's revisit the problem again and try to understand, right? Now think that if in this particular system, I'm presenting the system again, if the top part of this is fixed over here, now imagine that there is no PB over here. Suppose, let's just forget PB. There is a PA which is acting over here at this particular juncture, right? Now if my top is fixed, right? Imagine this is fixed, and if I am pulling at this particular point, at this particular juncture where my fingers are over here, these fingers, if I'm pulling over here, right, since the bottom is free, which pipe will get stressed? The top pipe will get stressed, because the bottom just simply will go as a rigid body motion, it will go. Right. Now on the contrary, when you are pulling this bottom with this force PB over here, then both the lower pipe as well as the upper pipe will undergo some amount of stress. Right? And again, to reiterate, suppose if you're just pulling with this force PA over here, only this pipe gets stressed, this pipe undergoes no stress because this pipe simply moves down, because this pipe undergoes some amount of stretching. Whereas when you are applying this force PB, since this is a continuous system, this pipe gets stressed as well as the upper pipe gets stressed as well. Okay? So the first question asks that find PB so that the tensile stress sigma in the upper part is 14.5 MPa. Right? Now we remember that from the discussions we had before, that we know that our sigma is nothing but P divided by A. This is the general formula of calculating the stress, right? Now we are calculating the stress, remember, for the upper pipe. So for the upper pipe, first we have to calculate what is the area of cross section, and also we need to find that, you know, what is the load, what is the P which is acting on the upper pipe over here, right? So to calculate that one, so for the upper pipe, right, if I calculate the A, it is going to be pi the outer diameter d2 square minus d1 square divided by 4, right? So this I have already calculated. So this value comes out to be, let me check, this value comes out to be 784.61 mm square,